Hello, my name is Troy Rain. I'm the data science lead for Caltech IPAC IRSA. This is part 2 of Cloud Data Access for the Euclid video series June 2026. In the Cloud Data Access part 1 video, we covered the basics of on-cloud data, including where to find it and how to access it, including this cloud access tutorial with examples for images and spectra. This video is dedicated to catalog data. We're going to look at these 3 Python tutorial notebooks. We'll go to this link. Here, we can see all of IRSA's tutorial notebooks. And here is the Euclid landing page. The Euclid Q1 catalogs produced by the Euclid collaboration are split into 3 groups, and you can see tutorials for those here. MER, PHZ or PhotoZ, and SPE or Spectra. And those comprise about 15 individual tables. IRSA serves all of that from both on-premises and on cloud. This merged objects HATS catalog is an enhanced data product that IRSA created by merging most of the data from those 15 tables into a single Apache Parquet database dataset. You can bulk download this catalog directly from IRSA if you want, but in most cases, we recommend using the on-cloud copy because you can query it without having to download the whole thing first, even in massively parallel data processing pipelines. You can see here that joining those 15 original tables resulted in this merged objects catalog having almost 1,600 columns, and there's 1 row per Euclid object. The Parquet dataset is structured as a HATS catalog, which we'll talk about more as we go, but basically it means that the data are organized spatially using HEALPICs. HEALPICs is a tessellation of the sky, so each partition, which you can just think of as a file, contains the data for all Euclid objects observed in a given HEALPICs pixel, which is a region of the sky. Section 4 describes this merged objects catalog contents in detail. It lists all the Euclid Q1 tables that were joined together, describes the column names, and links to the Euclid collaboration papers that describe the data. Here's the MER tables and the PhotoZ tables and the Spectra tables. In addition, there are a few columns that were added that aren't present in the original Euclid tables. The Euclid tile ID, and then some HEALPICs and HATS columns, which are helpful for spatial queries. This section defines Euclid deep fields using HEALPICs pixel indexes, so we can easily filter the data later using the HEALPICs columns that we just saw. And this notebook ends by showing a basic query using the Apache PyArrow library. When querying or loading data from HATS catalogs, we recommend using one of 2 Python libraries, either PyArrow or LSDB. And we'll look at 2 more notebooks, 1 for each of those libraries. This magnitudes notebook does basically 2 things. It shows how to use the PyArrow library, and it teaches about the different flux measurements that Euclid Q1 provides. Euclid Q1 provides several different kinds of fluxes derived from aperture, photometry, template fitting, PSF, Cirsic profile fits, and more. Each of these is good for different use cases. We're going to look at the template fit and aperture measurements. We want to work in magnitudes, but the data are stored as fluxes, which means we need to convert them. The PyArrow library is particularly good for this because it will do the conversions on the fly, meaning we don't have to load all the fluxes into memory first. The Euclid Photometry Cookbook gives recipes for converting to magnitudes depending on the type of flux measurement. So this function implements the recipes and returns expressions that will pass to Pyaro so that it can do the conversions for us on the fly. Here is where we define which columns we actually want to load. Some are simply loaded as is from the catalog, like this classification column, this PHC class variable we defined above. This is just the name of the classification, the column of classifications that was generated by the PhotoZ pipeline from Euclid. And there's also columns here that will be our magnitude. So here's our function that we just created. And here's where we pass in that function for Pyaro to create these for us. Next, we'll define some row filters. We are restricting to the Euclid deep field just for demonstration purposes. You can easily do an all-sky query by skipping this. We want to query for different types of objects so we can look at their magnitude distributions. These are cuts for quality and simplicity, and then we pass the Fornex deep field cut. Here we construct a Pyaro dataset object, which we can use to query the HATS catalog. That's this right here. This loads the Parquet metadata, which the dataset object will use under the hood to efficiently navigate the files and filter and load the data. Now we submit the query here. Here's the columns and the row filters that we defined earlier. This returns a pandas data frame. And here we see our data. Here's our magnitudes that Pyaro constructed from the fluxes on the fly, and the other columns that we requested, the classifications and so on. Pyaro is very efficient at executing queries and loading data, even with complex operations like we're doing here. But the upcoming Euclid Data Release 1 will have a lot more data than this Q1 release. And then you might want to add some parallelization in here so that you can load data from different partitions concurrently. That's pretty easy to do. And these bottom two NeoWise tutorials have some examples of how to parallelize with Pyaro. Section 4 and Section 5, the rest of this notebook, teaches about the Euclid flux measurements. It's based heavily on the Euclid collaboration's data papers, which are linked to. This section plots the template fit magnitude distributions of different types of objects. And then it points out a few different things to notice about them, and talks about a few things that the Euclid data papers discuss. The next section compares the template fit and aperture photometry measurements. The top row is extended objects, mostly galaxies. Here's the Y, J, and H Euclid bands. And this is template fit minus aperture magnitudes. The bottom row here is point-like objects. And then it discusses a little bit about the offsets that you see here. So you see a slight offset from 0 in most of these. And so it discusses that offset and talks a little about which type of measurement should be considered more reliable in each regime, extended and point-like, based on the Euclid data papers. Now, if we go down here to the techniques and tools section, we can find the tutorial that shows how to use the LSDB Python library to access these HATS catalogs. This tutorial describes hats in more detail. Um, and so there's this link here. In addition to the hats catalog, this Euclid merged objects product includes two ancillary data sets, a margin cache, and an index table. And the three of these together, the margin cache, index table, and the catalog itself, all three together are called a hats collection. You can access all three of those data sets using the IRSA library. A big advantage of the LSDB library is that it was written specifically for hats. So it knows how to use all three data sets under the hood. So you as a user don't have to think about them. Here we grab a hold of the entire hats collection using LSDB. This loads hats metadata. So no actual data has been loaded yet. So this looks a lot like a pandas data frame. It's actually a Dask data frame. But you'll see there's no data in here. No data has actually been loaded yet. We're just looking at the columns and the partitions that we have access to. LSDB is especially good for spatial problems like cone searches and cross matches. And in this notebook, we're going to cross match Euclid with ZTF. First, we'll restrict to the Euclid North deep field for the purposes of the demo. You can do an all sky cross match by skipping this part. Here we're creating a new LSDB catalog object for Euclid with the columns and the row filters that we want. I think we skipped the part where we looked at yep, here we go. Sorry about that. So here we are back in section 3, defining our filters. So we're restricting to the Euclid deep field. And here's where we create the cone search spatial filter, where we submit the Euclid deep field cone search. So this is just creating a filter, still not loading any data yet. The spatial filter we'll use down here when we actually do the cross match. So section 4 does something similar for ZTF. And now here we are creating a new LSDB catalog object for Euclid with the columns and the row filters that we actually want. Unlike with Pyaro, where you can reuse the same dataset object for all kinds of queries, with LSDB, you need to create a new catalog object anytime you want different columns or filters. It's technically possible to apply the filters after creating the catalog objects, but that makes it much less efficient. So it's much better to put these filters right in the LSDB open catalog call. And here is the equivalent thing, the equivalent catalog object for the ZTF catalog. Now we're going to define the cross match. It's very simple to define this cross match, but a cross match is a pretty complex operation. The LSDB provides this simple way for users to code it up, but then it handles everything else under the hood. So LSDB will actually use one of those ancillary data sets that we mentioned at the top of this notebook. That's the margin cache, and that gives LSDB access to. So LSDB is going to parallelize over partitions, and a partition is a region of the sky. But with the cross match, we want to make sure that we don't miss something that's right outside of that region, but is within our cross match radius. And so the margin cache ancillary data set holds all the data in the margin around each partition, so that when LSDB parallelizes over this, it doesn't miss those objects that are right outside the partition. It still has access to that data. But all the user has to do is this command right here, and then LSDB does everything else under the hood. We still haven't executed the cross-match yet or even loaded any data. We're just seeing this cross-matched catalog object, no data in here, columns and partitions. This section is where we're going to actually execute the query. Now, an important thing to know about LSDB is that it uses Dask under the hood. Dask is a Python library for parallel and distributed processing. This is creating a Dask client to manage the work that needs to be done. And so we're basically telling it here to use the same number of workers as the number of CPUs on the machine it's running on. And the number of workers determines the amount of parallelization. There are a couple of things to be extra aware of here. For threads per worker, 1 or 2 is plenty for most LSDB calls. Any more than that, and the performance tends to decrease. The most important thing is this memory limit keyword argument. Auto tells Dask to take the total amount of memory that's available on the machine and divide it between the workers. This ensures that Dask won't try to use more memory than the machine has. But the trade-off is that individual workers can run out of memory even when the machine still has plenty of total memory available. If that's happening too much, where workers keep running out of memory, the worker will run out of memory, it will shut down, and then a new worker will start up and try again. So if that's happening too much, try instead setting this memory limit keyword argument to none instead of auto. Then the individual workers can use as much memory as they want. What you need to do in that case is watch the total memory that's available on the machine and then reduce the number of workers if there's not enough total memory to complete the cross-match. Okay, finally, this Euclid cross ZTF.compute. This .compute is what's actually going to execute this cross-match. So now this Dask sends the work to all the workers. They execute the cross-match, and here's the data. So we see this spatially matched data from Euclid, got several Euclid columns here, and ZTF. Another thing LSDB provides a simple interface for is lookups by object ID. It uses the index table ancillary dataset to look up which catalog partition your object's data is in, and then it loads the data from the catalog. You could do the same thing with Pyaro, but you'd have to query the index table and the catalog separately yourself. Here, here we're opening a new LSDB catalog object with the spatial filter that we want for this one. And let's see, here we're getting the object IDs that we want. We're looking them up for something that we did earlier, but you may also be coming in with already knowing the object IDs that you want. And here, this example uses ZTF, but you could do exactly the same thing with the Euclid HATS catalog. Here is where we call the LSDB function ID search, and we pass in this list of object IDs that we want the data for. So under the hood, LSDB is going to use that index table ancillary data set. It's going to figure out which catalog partition the data for these objects is in. Then it's going to go to the catalog data set and actually pull the data. Again, we still haven't executed anything yet. Here is the .compute call that's actually going to execute this query. And then here we see the ZTF light curves that got returned. Here's the table of data. And then we can plot the light curves here and look at the light curve data that got returned. So that is Euclid Q1 catalog data on the cloud. Thanks for watching.